Okay, so let us finish what we started last class. We started by talking about some different concepts of the size of a set, and we defined this object that we called the Lebesgue measure it had a similar feeling to the idea of the Jordan content, but we made a couple important changes that meant that, of course, we could have infinitely many of these little intervals covering it, and suddenly this is defined for all kinds of subsets and defined in a nice way in that we can add measures of disjoint sets together for at least a bigger class of sets that we could take the Jordan content of. So now we want to use this to build up a definition of the integral that is hopefully a little more powerful than the Riemann integral. So what do we expect? Well, we already know the volume of a set. We expect that to be equal to what happens if we just integrate the function 1 over that set. So we expect this. Okay, if A is a measurable set, or an alternative way of writing this, I guess, would be to integrate the characteristic function over the whole real line. So remember, the characteristic function was this object that was 1 inside my set and 0 outside my set. Okay, this was true for Jordan content, but of course it only worked for sets that were Jordan measurable. But now we could straight away take a function like this. We could say, well, let's take the function that is equal to, say, 0 when we're looking at a rational between 0 and 1, and 1 if x is an irrational between 0 and 1. Right, and maybe 0 outside of this interval. And this is something that we could not integrate before. All right, we did upper sums, and upper sums would always give us 1, but lower sums would always give us 0. So there was just no Riemann integral. But here we can say, well, the integral of this function. Well, this is just the characteristic function for this particular set. So this is the characteristic function of the irrationals between 0 and 1. So we just expect that to be the measure of this set. And we said, well, the rationals take up no space, they have measure 0. The irrationals in that interval were everything else. By additivity, we said that was simply equal to 1. And suddenly we can do this integral very easily. In fact, it doesn't fall in the category of pathological things, it actually falls in the category of functions that are easiest to integrate. Okay, so that's the easiest thing to integrate, a function that is basically either 1 or 0. Okay, so what would be the next easiest thing that we might try to integrate? A linear function, maybe? Okay, linear function is a nice guess. No, we want to be able to, we'd ideally like to be able to come back to talking about putting things in terms of the size of a set. Linear function is a good guess. What else might be easy?
Area of a rectangle.
Okay, something that looks like the area of a rectangle, which I guess we can sort of do with something like this. So what's really happening here? Here, we've got a characteristic function we're integrating. What if we took a linear combination of 2 or 3 or some small number of characteristic functions? What would we have? We'd have a function that could only take a few different possible values, right? It could be maybe 1 in some places, 2 in some places, 0 in some places, but there's only finitely many things that we can make it. A function that takes finitely many values, we should be able to decompose into some kind of weighted sum of characteristic functions. And then if we assume the integral hopefully has properties that we expect, like we can pull constants out and it's linear, then that gives us something easy to work with. So let's try it next. Functions that take finitely many values. We're going to call these simple functions. Okay, so a simple function can be written in this form. Okay, so just some kind of linear combination of characteristic functions. Okay, where the lambdas are just some real numbers, and the AIs are some measurable sets. Okay, so then if we want to think about how we would define an integral, well, we start by saying, we're hoping the definition of integral we're trying to come up with should generalize what we had before. It should have the nice properties we had before, we just want to make it more powerful. So, if we try to integrate this, we might say, well, if we assume linearity, then I should be able to swap the order of the integral sign and the summation sign. I should be able to pull constants out of this. And all of a sudden, I have something that looks like the weighted sum of the integrals of a bunch of characteristic functions, the weighted sum of just a bunch of volumes of sets. Okay, and we got this just by assuming the integral should still be a linear operator like it always has been in the past. Alright, so I could certainly generalize this one a little bit. Maybe I give it a different value on the rationals. I say let's let this function be equal to, say, 2 on the rationals, 1 on the irrationals, and 0 everywhere else. Okay, and then if we try to integrate this, well, then we just have 2 times the measure of this set. Plus 1 times the measure of this set. Which in this case is still going to be 1 because, of course, this is still 0. And this part is still 1. So it didn't actually change the value of the integral in this case. But now we could start doing, arbitrarily more complicated things. As long as we have a finite number of these terms, we're kind of in business. Of course, we don't want to stop with piecewise constant functions or functions that only take finitely many values. We would like to do some things that are a little bit more interesting than that. But these are going to be our building blocks. Right? We've always had building blocks. For the Riemann integral, we had building blocks. Our building blocks were we know how to compute the volume of a rectangle, right? Basically piecewise constant functions. So this is a generalization of piecewise constant functions. It's not really piecewise constant because, I mean, this has discontinuities infinitely many places. But it's kind of the next best thing. It's piecewise constant in the sense that there's only finitely many values that we're worried about. And we're going to use those to try to get approximations of more complicated functions. So for more complicated functions, I'm going to draw it in a somewhat simple way because it's hard to draw functions that look like this. But we're going to take this and say, let's approximate it by simple functions. Okay, so, you know, a really crude approximation might be to just say, well, let's approximate it by one value. Or we could do better, say, let's try to approximate it by a few different values, and hopefully that's better, and so on. And we keep refining somehow. You know, there are some little technical details where when we do this and we start breaking it down in terms of simple functions, you know, we need to end up with sets that are actually a little bit measurable. So there's some little technical details there that you're not going to be able to do this with quite every function out there, all because some of them might be, for example, the characteristic function of a non-measurable set. But we can do this with a lot of functions. So what we're actually going to do, I'm going to start with non-negative functions. We'll get to non-positive functions or mixed functions later. Let's start non-negative. I have a function, and what I'm going to do is approximate this from below by simple functions. And we'll talk in a minute about why I'm choosing to approximate from below. Okay, so let's let f be non-negative, and let's approximate from below by simple functions. Okay, so it would be something like this. Simple functions that always lie below the function that I actually care about. Okay, and then, all right, for any given simple function, we know how to integrate it. We've come up with a definition of it. And for any given simple function, if we do its integral, we expect to be underestimating the value of our true integral. That means if we try all possible underestimators, we should be taking the supremum of these if we want to hit our true value. So there's a fairly natural way of trying to write down a definition. Okay, so I'm going to define the integral, and now I mean the Lebesgue integral of f over the reals Okay, so once again, we're starting with simple functions that lie below. They're all underestimators, so we need to take the supremum of these. Okay, and this is over all functions such that g is less than or equal to f and g is simple. The question so far? You know, it's the basic ideas are not too hard of concepts, I think. This, of course, importantly, if f happens to be a simple function, then this is going to be compatible with how we've already defined the integral of a simple function, right? Well, we have to look at all simple functions below f. The biggest possible one is f itself, and that's what we'll spit out in the supremum here. So that's just an important note. So this is compatible with our definition of simple functions. With our definition of the integral of simple functions. Now, another question which we will need to get to is, what happens if f happens to be Riemann integrable? Does this give us the same value as the Riemann integral, or does it not? But we need to build this up a little bit more. Any thoughts on why I started by asking f to be greater than or equal to 0 to do this? Yes?
Does it have something to do with the way we define the measures being infimum?
Does it have to do with the way we define the measures being infimum? It doesn't quite have to do with that. There's something else going on here. Yeah?
So the volume does not, let's say, because if you have the negative one, we subtract the volume.
Okay, so you're worried about adding and subtracting volume. So there's something interesting here. We can do this for some functions that we couldn't do Riemann integrals for. Do you remember what was one class of functions that we could just never do Riemann integrals for? Yeah, unbounded functions. So with this, if I happen to have a function like this that is unbounded, but it's bounded below, but it's unbounded above, I can still approximate this from below, right? A function, if it was unbounded below, I might have a hard time coming up with approximations from below. But being unbounded from above is not a problem. I can still come up with simple functions that will lie below this thing. Okay, so if f greater than or equal to 0 is unbounded above, I can still easily approximate it from below by simple functions. It's a lot more delicate to approximate something from below if that something is actually unbounded below. So this is really the reason that I said f is greater than or equal to 0. It doesn't even matter so much that it's greater than or equal to 0. I give it some kind of lower bound so that I know that there's always somewhere where I can stick a simple function below it easily. But this, okay, we already see there's probably a little bit more power here than there was in the definition of the Riemann integral, because a function like this, in principle, is no problem. Now the supremum, when we take the supremum, we might get infinity, of course. We're going to have simple functions that get arbitrarily high, and depending on what measure they're supported on, it might be big. But we can certainly write down this quantity. Again, does this give us the same thing that we are hoping to get? That's another question. Then if I want to integrate negative functions, I just flip it upside down. Okay, so if f is less than or equal to 0, then we could just say that, well, the integral of f is minus the integral of negative f. Okay, then negative f is now greater than or equal to 0. We use our definition, and then we flip the result again. No problem. Now, yeah?
So in this case, we can write every function as the positive.
Exactly what we're going to do. We're going to say, in general, a function that we care about may not be always positive or always negative. They have a positive part and a negative part. We're going to handle them separately. So if I have a function that is something like this, positive and negative, then I'm going to decompose it into two pieces. So the first part will be the positive part. Okay, so the positive part, anywhere that is negative, I just kill it. I set it back to 0. I keep everything that's above 0, and then I set it back to 0. Okay, and then separately, I'm going to say, well, when is this less than or equal to 0? If less than or equal to 0, we keep it. If it's positive, we kill it. If it's less than or equal to 0, we keep it. And this I'm going to call it minus the negative part. So this is equivalent to the actual negative part we're going to reflect here. And what is f itself? F is just equals to, well, this part that's above 0, minus this part, the part that was below 0. So f positive minus f negative. And here, f positive is just the maximum of f with 0. And the negative part is the maximum of minus f with 0. Okay, and then this gives us a way to integrate a generic function. So now we have that for a generic measurable function, this is just equal to the integral of the positive part, which was the supremum where we approximate from below by simple functions, minus the integral of the negative part, which again is just the supremum where we approximate from below by simple functions. And this completely allows for unbounded functions, for functions that have crazy discontinuities. And we're going to say that a function is integrable if it is measurable. So we don't want to have any pieces in here that look like characteristic function of non-measurable sets, essentially. Okay, and if the integral of the absolute value is finite. And there's another name for functions that have this property, which is a name you'll have probably seen before. So L1 is what we call the set of all functions who are integrable. And of course, this is now equivalent to just saying The positive part is integrable, and the negative part is also integrable. So f is integrable if and only if f plus and f minus are both integrable. Yeah.
In L1, the metric is integral.
In L1, yeah, L1 is the L1 norm. It's a norm on the functions, yes. It's just this integral. And of course, you can use the norm to symmetric. Okay, we get an important comparison property here, which will probably be useful to us. Again, our goal is, we know there are some things we can integrate this way that we couldn't integrate before, but we would like to say that we're not getting totally off the wall results on things where we could integrate before, right? You know, we built up that definition carefully. It was founded on a little bit of intuition. Intuition is great. You know, we want the results we have here to kind of match what happens when we go out into the real n-dimensional world. So we don't want to be getting off the wall results now. So let us start with this little lemma. That if f and g are both integrable, okay, and if they're ordered, then the integrals are also ordered. Okay, so I'm going to start by doing this for non-negative functions. Of course, then we know we'll break these down into two components that are both non-negative. Okay, so let's start with this. So let's start by assuming everybody is non-negative and they're ordered this way. Okay, we do know that this certainly works for simple functions, this kind of comparison, right? It's easy to show this kind of comparison works for simple functions themselves. So we just have to use that to show that it comes through in the limit. Okay, so what do we know here? We know that, so what is f? F is the supremum of all simple functions . Now, if I change the class of functions I'm taking the supremum over, let's say I keep all of these h's in here, but I add some more. Does the supremum go up or go down? Or stay the same? So if I have a bigger class of functions that I'm taking the supremum over, it will go up, exactly, right? Because, well, all of the candidates are still here, so the supremum of my original candidates is the still same quantity, and if there are new candidates that go even higher, then the supremum goes up. So if I enlarge this set, the supremum goes up. I can enlarge this set by considering simple functions that are allowed to maybe reach past f and reach all the way up to g. So this is going to be less than or equal to the supremum, the integral of simple functions that are less than or equal to g. Okay, and this is just because since f is less than or equal to g, this supremum is computed over a larger set. Okay, and this, of course, is just the integral of g. Okay, so this comparison works for non-negative functions, and then we should be able to extend it out to more sophisticated functions. Okay, so more generally, we just have that f is less than or equal to g. Okay, and that means that minus f is bigger than or equal to minus g. Minus f is important because minus f is going to show up here. Right, so in general, if we look at this, well, what happens? The positive part of f is equal to the max of f with 0. F being less than or equal to g. So this is less than or equal to the maximum of g with 0, which is the positive part of g. So the positive part goes up. And then similarly, we can compute the negative parts. The max of minus f with 0. Now we're going to have inequalities facing the other direction. Minus f is bigger than or equal to minus g. Okay, so we get the negative parts are ordered the opposite direction. Okay, so I can put these together to say, well, if I integrate, the positive part is a positive function, so this result holds. So if this part is less than or equal to this, then the integrals. Okay, and similarly, the integral of the negative part is going to be bigger than or equal to the integral of the negative part of g. And then we put it all together. We say, how did we define the integral of the complete function? It was the integral of the positive part minus the integral of the negative part. So the integral of f was the integral of the positive part minus the integral of the negative part. Okay, this integral is less than or equal to the integral of the positive part of g. Now here we have the reverse inequality, but that ends up being a good thing because we also have a minus sign in front of it. So minus this integral is less than or equal to minus this integral of the negative part of g. And indeed, we get the comparison result that we wanted. Okay, so, I mean, it's a simple result. It's an obvious result, probably. But we know by now that we shouldn't be tricked by things that seem obvious. Okay, so the big question is, have we just created an extension of the Riemann integral, a generalization, or have we created something completely new and different? And now, when we're doing any kind of physics or engineering, we have to decide which integral is actually the physically meaningful one. So the good news is we've done something consistent but extended it. So I guess there's two parts to the question here. Is the Lebesgue integral consistent with the Riemann integral? When they're both defined? And secondly, is one of them more powerful? I mean, we've seen there are functions we can integrate now that we couldn't integrate before with the Riemann integral. But it's possible that the other way around holds too. It's possible that there are some functions we could integrate using the Riemann integral that we now somehow can't accommodate. So is one of these definitions more powerful? Okay, so here's the big result, which is an important result, and it will turn out is not going to be too painful for us to prove. So let's suppose I have a Riemann integrable function. On some interval. I mean, we know this is one restriction of the Riemann integral. We need a bounded function defined on a closed bounded interval to get off the ground. So there are certainly things that we can do now we couldn't do before. The question is, can I construct, well, will I get the same answer here, but also can I feasibly construct a Riemann integrable function that I can't do with the Lebesgue integral? All right, so we have a Riemann integral function, and I'm going to let I sub r denote the value of the integral. Right? I have two working definitions of the integral right now. I don't know yet if they're equivalent, so I need different notation for them. So I'm going to call this I sub r. Okay, and the result is that actually automatically this function is Lebesgue integrable, and when we do the integral we get this number. So it's what the theorem is what we want, that we've created an extension, a generalization of the Riemann integral. Okay, so then f is automatically Lebesgue integrable, and the integral is equal to IR. So this will be the value of the Lebesgue integral. Okay, so how are we going to prove it? I guess we'll take our usual approach of starting by writing down the things that we know. So we know that this function is Riemann integrable, and we know its value, right? So we know that all Riemann sums, and in particular the upper and lower sum as bounds on them, can be forced to be within epsilon of this as long as we partition things finely enough. Okay, so let's pick an epsilon. Okay, we know that there exists a partition. Okay, we're back in one dimension, so we can kind of write out our partition explicitly without too much pain and suffering. Okay, such that on this partition, we get our upper sums and lower sums within epsilon of the value of the actual integral. So the upper sum, the upper sum is bigger than or equal to the value of the actual integral, but I can get it within epsilon. So just by subtracting epsilon off of this, I can make it less than or equal to the value of the Riemann integral. Right? course, this is always less than or equal to the upper sum, and this just says, but it doesn't differ by more than epsilon. And then similarly on this side, okay, I have lower sums, which itself is going to be smaller than the value of the integral, but as soon as I add epsilon to it, I'm in business. Now what do I need to do? I need to define, I need to start approximating this thing from below by simple functions and try to show that that somehow gets me also arbitrarily close to this number. So I wrote down what I know, okay, right, and which we can refine the details of that as we see what's needed. But now what I really need is to start constructing simple functions. I want to construct the value of this integral and show that it gives me what I want. Okay, so let's try to define a simple function. Any thoughts on how I would come up with a useful definition of a simple function here? Yeah.
Just evaluate f at points of the partition.
Okay, evaluate at the points of the partition. Okay, so that's a good starting thought. We should use the partition that we already have, right? We have an obvious breakdown into little sets that we can easily compute the measure of. Do I want to evaluate it at the points of the partition? I need an underestimator. That's what I really want, a simple function that underestimates f. So I should take it at the lowest point, or if there's no minimum, I should take the infimum. Okay, so let's define it like this. I'm going to start by defining it. Right, this partition breaks things up into intervals. I'm going to start by looking at the open intervals, right? Because the endpoints are part of two intervals. I have to uniquely define g by some value at this endpoint. So let's define a simple function g by, so if x belongs to one of these little intervals, okay, then let's just let g of x be equal to the infimum. In fact, I'll do the infimum over the closed interval. There's a reason I'm doing the infimum over the closed interval.
So it can exist.
Well, certainly so it can exist. I mean, the infimum can still exist over an open interval, but not only so it can exist, there's a special name that we've had for this, special notation we've used for this particular quantity before. Right. That's right. This object here plays a very important role in this object right here. This is just my little mj that shows up in my lower sum. Right, that's good. We need a simple function, but we want a simple function that somehow relates us back to things we already know. This relates us back to things we already know. And then, okay, and importantly, this is indeed an underestimator. Then at the endpoints, I just have to give it the value of an underestimator. Now, we perhaps know that for a simple function, when we're doing the Lebesgue integral, there's only a few endpoints, right? Finitely many. What's the measure of the set of endpoints? Zero, right? So the endpoints take up no volume. It doesn't, in terms of the value of the integral, it doesn't really matter what value I assign to this function, right? It will be that number times some set that has volume 0. So I just need an underestimator. So if x equals xj for some j, let's keep it simple. And let's just use the smallest value of the function. Okay, and we'll call this just little m. This is, of course, also less than or equal to f of x. Okay, so I've got an underestimator. And that means I have a lower bound on the possible values of the integral, right? Because the integral is going to be the supremum of all of these guys. So let's explicitly write g as a simple function. G takes, okay, finitely many values. It takes all of these mj's, there's finitely many of them, and then it takes this lower bound m. Okay, so we're going to be able to write this as, okay, all of the mj's times the characteristic function of the interval xj minus 1 to xj. Okay, so if we then in this open interval, we just take the value mj, otherwise it's 0, it goes away. And then if we happen to land at one of these endpoints, it takes the value m, so that's m times the characteristic function of just the union of these endpoints. And now this is something that we can integrate very easily, right? So since g is simple, right, what is this going to be? This is going to be the sum of mj times the measure of this interval plus m times the measure of our set of endpoints. Okay, which is, well, intervals are easy to work out the measure of. We checked last class that this does the thing we expect, just gives us the length of the interval. This is a set of finitely many points. So this is going to have measure 0. And suddenly, we've done what we hoped to do. We've related it back to things we know about the Riemann integral. We've recovered this lower sum right here. And we know something about this lower sum. We know it's bigger than or equal to the value of the Riemann integral minus epsilon. Okay, so that means the value of the integral of f that we come up with, any candidate for that, has to be bigger than or equal to the integral of g, which is bigger than or equal to the Riemann integral minus epsilon. And this is certainly true for all epsilon. Since it's true for all epsilon, as we let epsilon go to 0, we get a nice lower bound on the value of our Lebesgue integral. I could have run the argument the other way around. So I chose to approximate f from below by simple functions and then use my comparison result. But my comparison result would also work if I approximated f from above. So I could have also approximated f from above, and I would have gotten my capital M's here. I would have had some reversal of inequalities. I would have recovered an upper sum here. And I would have gotten, okay, with the reverse of inequalities, the bound going the other direction. So using the same argument, okay, but approximating f from above, okay, and then using the comparison theorem, we get the reverse inequality. So indeed we find that we get the same number coming out either way. So this is good. I mean, this is good. We haven't created some kind of new nonsense. We're not just playing mathematical games here. We're consistent with what we've built before, which we built based on some reasonable ideas about how the actual physical world works. Because here we're just integrating on R, and our intuition works a little bit on R. Okay, so what's the conclusion? If f is Riemann integrable, then f is Lebesgue integrable. Okay, and we get the same values. But of course we know the converse does not hold, right? Lebesgue integrable doesn't mean we can do a Riemann integral. Questions? It's not too bad, right? It's a topic with a scary name, but at least seeing the ideas of where all this stuff comes from is not so bad. All right, what else can we do here? All right, I'm basically done proving things, but I will give you a couple other little interesting nuggets. So a really important result is called the dominated convergence theorem. Okay, so the idea here is we're doing function approximation. We have a sequence of functions that is converging to something. And we want to know, well, if we do the integrals, do the integral of these functions converge to the integral of the result? Now, these may not be continuous functions, so we may not be talking about uniform convergence in the sense that we've done before. So things we know about continuous functions on closed bounded sets, okay, that doesn't hold here necessarily. But there are still cases, and we've seen cases, I think last semester we saw a case where we could have a sequence of functions that converged to something, but the integrals didn't converge. Right, I think I created a hat function that got taller and skinnier and basically converged to the zero function, but we kept the integral, the value of the integral always at 1. But there are cases when you can do this. So let's suppose that we have G, F1, F2, this whole sequence that are all in L1. So they're all integrable. Okay, and importantly, this function g is going to act as a bound on the rest of these functions in the sequence. Okay, and the result is that if the sequence of functions converges pointwise, okay, so we're not talking about uniform convergence. We can have weird things happen. Then this is enough to tell us that actually the limiting function is also integrable and the values of the integrals converge. Right, so we could certainly break this property. We could have sequences of functions that converge pointwise, but the integrals don't converge. It's not hard to generate those. One way to avoid that was to say, all right, let's force some kind of uniform continuity. That will avoid this problem. But another way to avoid this problem is to say if everything in our sequence is bounded by an integrable function, then we're okay, we're safe. So, I think one of the examples that we've seen is like this little hat function where maybe this is equal to 1 over n, and maybe this is equal to 2n, and maybe a hole there, and plug it back at 0 here. Right, and if we integrate this guy, integral of fn is equal to 1. Right, it's just the area of this triangle. But fn converges pointwise to the 0 function. Right, at the origin, I defined it to be 0. Any point greater than 0. Well, if I get far enough along my sequence, this triangle moves in, and eventually the functions all become 0 there. So these just converge pointwise to 0. And of course, the integral of 0 is 0. Right? So this is a case where the sequence of functions converges pointwise, but the integrals don't converge. The dominated convergence theorem would tell us stop, or we may be in a danger zone here. And it would, on the flip side, give us conditions where we know we're safe. We know that we can trust the values of the integrals, right? And the problem in this case, of course, is that I'm not going to be able to find an integrable function that is above everything in the sequence. The sequence is blowing up to infinity. I need something that stays kind of arbitrarily high, that always stays above these. Okay, so here, fn converges to f, but the integrals don't converge. Okay, but this, of course, does not satisfy the hypotheses. Another thing we may want to do is build different function spaces. So far we've talked about L1, the functions that are integrable, and the norm, as was pointed out, is just the integral of the absolute value of the function. As we've done before, we can change these to different LP norms. We've certainly done this with vectors. We can do it with integrals. Okay, so we can introduce LP spaces for functions. Okay, with p going from 1 to infinity, just like we did before on Rn. Those were vectors, so we had sums. Now we have functions, and we're going to do integrals. So you define it the way you expect. It's the integral of the pth power, and then raise it to the 1 over pth power. Okay, and LP then is just the space of functions whose p norm is finite. What happens if we take p to infinity? You're guessing the supremum. So when we did this on Rn for vectors, we took p to infinity and we got the maximum. So the obvious thing to expect here is that if we take p to infinity, we should get the supremum. You're almost correct, but not quite. But it was the obvious. It was the obvious first guess. Let's do an example. All right, I'll take a simple example, which will do what we expect it to do, and then we'll change it a little bit. So let me just take a simple characteristic function. It's 1 between 0 and 1 and 0 otherwise. Okay, the LP norm of this is very easy to compute, right? I just take the integral, integrating this over all R, there's only contributions from 0 to 1. 1 to the pth power. And of course, all of these LP norms give us 1. And we take p to infinity. It's just going to be the limit as p goes to infinity of 1, which is still 1. And that is our maximal function value, our supremum. It's what we expect. So, not so exciting. So let me change this example a little bit. So almost the same. F of x equals 1 from 0 to 1. Oh, let me leave off 0. I'm going to change the value at 0. I'm going to give it the value 100 at 0. And 0 everywhere else. And now let's work out the p norm of this. This is a simple function, right? And when we raise it to the pth power, it will still be a simple function. Okay, so what am I looking at? I'm looking at 1 to the pth power times the measure of this set plus 100 to the pth power times the measure of this singleton. Well, of course, for any fixed p, it doesn't matter how big p is. All right, this might be a whopping big number here, but it's multiplied by 0. So this is still just 1. right? Changing the value of a function at one point does not change the value of its integral. And if I take p to infinity now, okay, it's still 1. But that is certainly not the maximal or supremal value of this function. So the truth is that you are very close in your guess, that we should get the supremum. We get almost the supremum. Okay? You know, if we had a nice well-behaved function, we would get the supremum. But for any well-behaved function, if I change its value at a few points, I'm not going to change the value of the integral. So the p norm will not change, even though the supremum changes. Yeah?
Can we take the supremum over the point that they don't have 0 content?
So essentially, that's right. You take the supremum over most of the points. So this is called the essential supremum. So let me give you a little bit of language. Okay, so let's suppose p of x is just some statement. Okay, it might be the statement that f of x is equal to 1. It might be the statement that f of x equals x squared. It might be the statement that f of x is less than g of x. It's some statement about a function. Or some statement about points on the real line, really. Okay? If p of x is true everywhere except on a set of measure 0, okay, so we collect all the points where p of x is false. We look at the measure of that set, and it has measure 0. So maybe this proposition is false only at one point. Maybe this proposition is false at all of the rationals. In any case, it's false some places, potentially, but not very many, only on a set of measure 0. So if this is true everywhere except on a set of measure, we say that p of x is true almost everywhere. And we write it AE. So almost everywhere sounds like some kind of really fuzzy, hand-wavy language, but it actually is mathematically precise. It means everywhere except on a set of measure 0. So in the case of the infinity norm, we're going to look for bounds for f. So let me give myself a little space here. We're going to look at all f that are upper bounds. Now, normally, when if we think about the supremum, let me take the absolute value. The supremum, we would take all possible numbers that are always bigger than or equal to f, and then we would say those are all overshoots, so we take the infimum of them. I'm still going to do an infimum here, but I'm going to make one exception. I'm going to say this doesn't have to be true everywhere. This has to be true almost everywhere. So we find the collection of numbers that are always bigger than f, except maybe on a set of measure 0. I take the infimum of those, and I get what is called the essential supremum here. In this case, right, the essential supremum of this would be 1, which is coming out as our infinity norm here. So this is the essential supremum. Right, and again, the big picture is that changing a function at a small number of points, or even infinitely many points if it has measure 0, doesn't change what happens in the integral. The integral doesn't see changes on that scale. Yeah?
Does this work for convergence?
Does this work for convergence? So the dominated convergence theorem, I think, requires a bounded above everywhere. Is that your question?
I mean, the statement that if...
You can talk about convergence almost everywhere.
Let's say Px is the statement that xn converges to x, let's say.
Okay. So let's see. P of x is a statement that we can come up with a sequence that converges to x, for example.
No, let's take the functions. With fn converges.
Okay, it's a statement that fn converges to f. Yeah, then we could say that this is true almost everywhere, certainly. Right, so, I mean, if I'd had, for example, if I changed this example a little bit, before I plugged the hole at 0, right, and now I leave it up here, then I guess this fn converges to 0 now almost everywhere. But blows up to infinity at this one point. So yeah, you can talk about that in terms of convergence. And we often would. When you start doing results in these LP spaces, and you want to translate that to what's going on point-wise, the best you can do is almost everywhere, because you know that changing things at a few points here isn't going to change what happens in, as far as LP sees it, but it will change maybe what happens point-wise. So almost everywhere language becomes really important when you're working with these integral spaces. Other questions? All right, it's a little bit early, but I think I'm going to leave us here today.